let's look at some examples of student T. These are a couple I assigned. So 10.1 says, let's hold it up here. Find the following T values in table 4. We'll just use our tables. And then it gives us, I picked B. All right, so we have T sub alpha, which is 0.025. That's what's given. I'm going to redo that. 0.025. And it gives us degrees of freedom. Degrees of freedom is equal to 8. So that means the sample size was 9. So you automatically would know that. All right, so that's pretty straightforward calculation. So let's go take a look. Now the tables, I already highlighted them, so it's easier when you see them, but it's makes it just a little nicer as I went. So here's the table. So this is the tables that are posted. So there's your standard normal, right? Your z-scores summed left to right, negative all the way to positive. No degrees of freedom. That's probably why they only do the right side for the z-tables. Okay, so there's t-distribution, and the value was alpha was 0.025. So this is degrees of freedom. This is your alpha. Okay, or it could be alpha over 2 if that's what you're looking up. So it's 0.025, right? So it's this column, and it said degrees of freedom was 8. So you go across, there you go, 2.306. So you come back to lecture notes here. So that means your T statistic is equal to 2.306. So that would be, for any of those values. Okay. Well, that's the simple case, simpler case, I guess. Okay, let's do 10.2. So 10.2 says, find the critical value of values of T that specify the rejection region in these situations. So 10.2, I didn't assign this one, but it's very similar stuff, really. A two-tailed test with alpha is 0.01. Okay, so two-tailed, so I wrote some of this down for you. Two-tailed. And alpha is equal to 0.01. And your degrees of freedom given to be. And it's probably not like, you're not supposed to say equals, but you can. It's okay. Degrees of freedom equals 12. Yeah, that's A. And I knew I was forgetting something. When I have to look close at things, oh yeah, I need these. Can't see anything when I look up, but so degrees of freedom are 12. Okay, good. And what do we need to do next? For two-tailed, we need to take alpha and divide by 2. Okay, so do that division and you'll get 0.005. Okay, so that makes sense. Okay, degrees of freedom the same, so that's what we're looking up. So let's go to our tables. We are concerned with this one. All right, so it's this column, and degrees of freedom was 12. You can see I already highlighted them. Was 12. So that's our test statistic. And if you get a little confused on the whole thing, graph it. Just do a bell curve, plot it, figure out. And remember, it's the numbers are higher when you go left to right, or bigger negative left, bigger positive right. and it's 0 in the middle, right? So it's like a number line, right? Then figure out where. That's how you figure things out. Don't do it all in your head and guess. Draw a table, plot these things. Best way to do it. I'm a visual person, and that helps a lot. So our test statistic is 3.055. So we come back right here. We say T is equal to 3.055. So if you're kind of used to looking at some of this, you can see that's a bigger number. It's a pretty large number. See, that's not just like standard deviations from the mean. This is a different distribution. Okay, let's move on. I kind of wanted to hit each case for you here. So D was 10.2D was, wait, did I do D next? Yeah. I want to do left tail to see what that looks like. A left tail test with alpha 0.01. So I wrote that down. Write stuff down. So left-tailed alpha is equal to 0.01. Degrees of freedom is given to be 7. Okay. So left-tailed you do not divide by 2. So we looked that up on our tables. 0.01. Degrees of freedom is 12. Wait, was that right? Yeah. 0.01, 12, and it's, I didn't highlight that one, huh? 2.6. Oh, I remember what I'll show you. Oh, I'm sorry. Degrees of freedom is 7. That's what's messing me up. But this was a left-tailed test, so technically it would be on the left to be negative. But you can't look that up here, so you have to just make it negative. So degrees of freedom are 7, and it was where was it? 0.01. Yeah, I highlighted correctly. It's just hard to see it right there. So get a ruler out, and just kind of line it up, make sure you're picking the right one. So there it is. So 2.998. But do you report the 2.998? So this is the part I want. Why I picked left-tailed. So left-tailed for this one, your test statistic is T equal to, but it's left, so you change it to a negative because it's all symmetric. So it's negative 2.998. Okay, so that's how you handle that. Okay, let's do 10.3. This one a little tricky. 10.3a. Looks like I assigned this one as well. Use table for blah 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 to approximate the p-value for the test statistic in these situations. So this gets a little tricky because you can't find the exact number. So a two-tailed test with t equal to 2.43 and 12 degrees of freedom. I suggest every time you write that stuff down. So two-tailed. So we'll say two-tailed. And it's given that t is equal to 2.43 and your degrees of freedom is equal to 12. So this is where we have to think about it. Two-tailed test going like this on either side. So we're looking at the probability that t is less than negative 2.43 plus the probability that t is greater than 2.43. So you're on either side, but it's a symmetric case. So left side and right side are equal. So you can say, when you look this up, that this is equal to the probability, almost messed it up. This is equal to 2 times the probability that t is greater than 2.43. So that's what you can look up. So when you do that, you look up 2.43. Okay, so let's look up that. So we're looking at degrees of freedom is 12. So we're here. And we're looking for 2.43. 12, so so it's between these two. Right there. So 2.3 and make sure I'm doing that right. 2.43. So so that's the keys. You have to go to degrees of freedom 12. You can find 2.43 somewhere else down here. 2.4. Where did it go? I found it once before. Right here. Right, so it can be right here. It's between those two. Oh wait, but that's the wrong degrees of freedom. So you got to go to degrees of freedom 12 and look that up, and it's basically between these values, 2.30 and 2.68. So what I did, right there, it's got to be between 2.02 and 0.01. Okay, so go back. You have so basically, and that's times 2. Where's my calculator? So, and you got to multiply by 2. So let's see, where did it go? There it is. All right, so when you look up in the tables, it was this. So so you're interpolating those two, and then times 2 basically. Let me see what I have written down. 0.01, 0.05. Yeah. So 0.02, 0.01, add to divide is 0.015. So if we used 0.015 and then multiply by 2, that's 0.03. So basically what you're saying then, or what we can say, is that this is approximately 0.03. But you don't know exactly where it's at. So the best we can say is that it's between 0.01, and this is the p-value, and 0.05. Because if you look up 0.03, okay, so, and then you multiply this one by 2, so 0.03 isn't on here either. So 0.03 is between these values. So that's what you report. It's got to be some probability between 0.01 and 0.05. Okay, so that gets a little strange. So do a couple of those and kind of see what that means. Let's see, we're on 15 minutes. Let's go ahead and keep going. Do the next one. All right, so this one, you may want to use a calculator, or I used Excel. I'll try to show you that as well. I didn't do the test statistic or anything on Excel. I just did the mean and standard deviation. So this is given. This is an example, but I didn't put all the garbage in there. I just told you what it is. So find a 95% confidence interval for the mean of the data. Okay, so here's the data. Write all that in and calculate x bar, and then n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is 10. Oops, change that back to white. N is 10. Degrees of freedom is 1 less. That's all you do. Okay, and you can calculate x bar and all that. I calculate x bar to be 60.8. And I got, in Excel, I calculated the sample standard deviation. It's always going to be sample for this stuff. 7.9694. And it's probably worth showing you. Going to here. It's actually in this one, I think. Sheet 6. Okay, so this is what I did. I can't point on this one, if you recall. So I wrote out the data, right? Put all those down, right? And then I just did the equation. I said equals, and I typed in mean, M-E-A-N. Nothing came up. And I realized, oh, duh. In Excel, they say average. Everything else is really sophisticated, so I don't know why they use mean, but I had to do that anyway. And then we go to that. That's standard deviation, and it's .s. The .s means sample, and so you do the sample, and you can see it's A11 through A20. Okay, so I don't know why I put it down that far, but that's what I did. Okay, so I just calculated those. I wouldn't make you calculate by hand the standard deviation. Okay, so that's how I wrote those down. And now I can do the test statistic. So let's see, a 95% confidence interval. So that means your alpha is equal to 0.05. Right, so it's that. Those are the n's for your alphas. Okay, so this represents the length of a sea animal. That it was like some crab, or I forget what it was. Right, so it calculates your test statistic, or not. I'm sorry. You calculate your t. What is 2.262? Because it's alpha, so it's 0.025. So I'll show you 0.025 here, and degrees of freedom is 9. 0.025 right there. 2.262. There, that's what you're using. So 2.262. Okay, good to go. Degrees of freedom, I already had that down. That was 9. And then I did this individually, separated it out, calculated the standard deviation using a computer. So it's 7.96. I just used 3 decimals, 9 over root 10. Did that calculation, and I get 2.520. And then I do the confidence interval, which is x plus or minus t, which is your 2.262, times your test statistic. And yeah, that's your S over root n. And so that whole thing would be your test statistic. But so I'm doing confidence interval, which is that. So I'm doing this right here. Okay, so that's what I got down there. Put in the number 2.520. 0.520 and calculate that out. I use 1 decimal because these are all whole integers anyways. And so I got x bar plus or minus 5.7, which is equivalent to that symbol. Actually, the double arrows is if and only if, technically. So I did this in my calculator. I added, subtracted 5.7, and this is the 95% confidence interval. I got 55.10. What was the mean again? Yeah, the mean was 60.8 to 66.5. Okay, so there's your 95%. So it's saying 95% of the samples, which in this case this is a very classic small sample case, because this was like sampling crabs or something. I don't know. But you obviously can never get the population. And it may be very impractical in this case. You know, if you're sampling, I don't know, tunas or something, getting 30 is probably not a big deal. Or tiny, I don't know, whatever, you're, bait people, probably not a big deal. But for these, it can be. So getting this many is all you're going to get. 10 is all you're going to get. So this is a classic case where you cannot get the population. A small sample is what's reasonable. And then I always want you to do this. Anything in mathematics, word problems, is, does it make sense? Does this confidence interval make sense? Does it look like it worked for this data? Okay, and so it goes down to 55 points. Is there anything below that? Yeah, here's one below it. Here's another one below it, but everything else is in the interval, or on the other side. Anything above 66.5? Well, it looks like it's just 78. So there's only 1, 2, 3 data points in this case that are not in the interval. So it's reasonable. It's a reasonable confidence interval. This guy right here, the 78, is probably an outlier. So that's out there, right? The 50 is closer, right? I'm not sure the actual numbers, but again, it seems reasonable. So if you only saw that like 2 of them were actually inside that interval, well, then it's wrong. It can't be that. Okay, so those are the things I want you to consider. Next question is in the solutions, which many of these are, of course. So do 10.5, work that out for your hypothesis testing, and any of these questions could be just give me the answer in the quiz, so make sure you write them all out, etc. Okay, and that should do it for our introduction, small case, simple cases for the student T, small sample hypothesis testing and interval confidence intervals.